The first one, here's what we're going to do for a bunch of these, at least at the beginning, is we are going to rewrite them, as I said. But then we're going to fill in the answer. So we're going to rewrite them down here. So this would be like a to some exponent equals a. So what would I fill in the box that would make this balanced? Hunter? 1. So that means it evaluates to 1. And if you didn't quite catch that, because this has an exponent of 1 on it, right? So same base, they have to have the same exponent. So that's how this game works. So again, a to what exponent gives us 1? 0. So if I continue to be a to what equals a to the 0, which gives me 1, right? Equating the bases. So if I put a 0 in here, I'm going to put a 0 there. But here's my point. On a test, you wouldn't change, introduce an x and say a to the x equals 1, therefore x equals 0. No, I want you to just say log base a of 1 equals 0. Or if the question was something like, what's log base 5 of 1? It doesn't matter what the base is, right? That's what the a represents. So that's just equal to 0. If you have to rebuild that in your head or on paper off to the side, fine. But we want to just say, hey, that's 0. Not using change of base formula, nothing like that. We want to know it as one of the laws. This is a really powerful one. So let's rewrite it. A to what exponent equals a to the x? So it's x. But again, if we get rid of all the bottom stuff and we just look at that line, log base a of a to the x equals x. So if you're taking the logarithm of a power and the base of the logarithm is the same as the base of the power, it all evaluates to the exponent of the power, right? The bases, cancel in a way. That's a big one. It's useful in rewriting things. It comes up in all kinds of areas. Okay, similarly, sort of, a to the exponent log base a of x. So since this is written in exponential form, I'm going to rewrite it in logarithmic form. And so I get log base a of what equals log base a of x. So again, it's x. Like if you recognize it, how easy is that one? But I'll tell you this. Usually on the test, like half the people get it wrong or just leave it blank or don't know because they just don't recognize it, didn't really spend enough time thinking about it, remembering this one. And these ones we get used to rewriting, but that one just doesn't stand out to us as obvious as how to figure it out if you don't know it. So it's worth really trying to click with this one and recognize it's very similar where you have the same bases, but make sure you know that one. Any questions? No? Okay, so that was sort of 4 simple properties of different kinds of logarithms, different situations you might find yourself in that'll be useful for some of the other stuff we're going to do right here. Anybody have an idea about what we can do with this one? Yeah, Natasha. Nice. Yeah, multiplying powers with the same base, so we can add the exponent. So this is equal to log of 10 to the 5. What's the base? 10. So what does this resolve to? What is this? 5, right? Base 10. We need to know that. That's something we need to know. And that's what we just did. Where was it? There, right? Log base a of a to the x, log base 10 of 10 to the 5 equals 5. Now, I want to suppose something. Just watch. Don't have to write this down. We have different little things that we can do, like the square root of 5 times 3 equals the square root of 5 times the square root of 3. The square root of 5 plus 3 does not equal the square root of 5 plus the square root of 3. So sometimes this works and sometimes it doesn't. Different properties, it depends on the situation. So I wonder if there's something we can do with this. So let's see. If I do log base 10 of 2 and log base 10 of 3, what's log base 10 of 10 squared? 2. What's log base 10 of 10 cubed? 3. So I don't know if you're following this, but these should be equal. Both of these, I started with the same thing, here and here. So they should be equal. So if one of them was 5, if I want this one to equal 5, does anybody see the operation that we should put between the two that will make it work? Alicia, what do you think? Addition. Very good. I can't believe you noticed that. Right? A different way. That's like a different kind of exploration of a property where we sort of just split them up, started doing what we could, and then thought about what operation would make it true. So if I look over at those square roots, the square root of 5 times 3 is equal to the square root of 5 times the square root of 3. It's not quite the same as what we did here. Because what we did here is not log of 10 squared times log of 10 cubed is equal to the log of 10 squared times 10 cubed, right? It's not quite the same. The operation changed, which is maybe somewhat new, but it's sort of similar, well, it's very similar to exponents, where if you're multiplying powers with the same base, you add the exponents. I mean, it's very similar to that, right? Okay, now, this is called the product law of logarithms, so let's prove it. We're going to do a couple of proofs here. And to make these proofs nice, we're going to start with something that you wouldn't really expect necessarily. So x is going to equal log base a of m. And I can rewrite that as a to the x equals m. And I'm going to start with y equals log base a of n. So therefore a to the y equals n. Everybody okay with that? Okay, so I'm going to come over here and I'm going to get m times n is just equal to, based on what I did over there on the left, a to the x times a to the y. That has nothing to do with the line above it. Maybe I should have moved it down a little bit more. That's just this times this is equal to that times that. So what can I do here? I can do m times n equals a to the x plus y, right? I'm going to take the log of both sides. I'm going to take the log base a of both sides. So this is log base a of m times n. Taking the log of something is just like multiplying both sides by 2 or adding 2 to both sides of an equation or taking the square root of both sides or the cube root of both sides. Log base a of both sides, same thing, right? It's an equation. So as long as I do something to one side, I do something to the other. So this is log base a of a to the x plus y. So what is that? What is the right side of this equation? Alex? Say that again? Not exactly. Sure. X plus y. So log base a of mn equals x plus y. But what is x and what is y? Let's go back to the blue and the green on the left. Log base a of m times n is equal to x, which is log base a of m, plus y, which is log base a of n. And that's what we were trying to prove. So now you can see it was convenient to let x and y be those things because it made it work out. Any questions about that? So that's a law that you need to know. Big one, yep.
So why can't you just, from the beginning, just quickly expand it and say that log
That's the law we're trying to prove, if that's what you're thinking.
No,
So, okay. So, similarly, we're not going to quite do this one as long. What do you think would happen when I divide? Yeah, very good. So this is going to be log base a of m minus log base a of n. The proof would work out similarly. Any questions about that? So there's another law that you need to know. And the last one, the power law for logarithms. So we're going to prove this one as well, and we'll start with let x equal log base a of m, and that means m equals a to the x. Okay, so then if I take what we started with and I get log base a of m, but which is actually now a to the x all to the n, right? This is equal to log base a of a to the x to the n. What do you do? This is the power rule. exponent of an exponent, like power of a power. So we multiply the exponents. A to the x times n. So what is this equal to? Just x times n. Is that right? That's one of the ones we just did. Log base a of a to an exponent equals the exponent. Look back up the page a little bit if you're not sure about that part. And careful, this is a really tricky step. This equals n times x. But what is x? X is log base a of m. So log base a of m to the n equals n times log base a of m. That's a big one too. Do you understand what it's saying? So for example, log base 2 of 16 squared. I can take that exponent and make it 2 times log base 2 of 16, which is 2 times 4, which is 8. 16 squared is 256, and 2 to the 8 is 256, right? So it's like either way you look at it, it's the same thing. It's kind of neat to think about it in different ways, be able to resolve it in different ways. This requires easier computational math, I guess. You could do it more easily in your head. Any questions about that? All right, what do we have next? So let's use a few of these and start doing some evaluating. Notice how it says evaluate each of the following using logarithm laws. Not change a base formula. In this case, using your calculator, you could just punch it in. How do we demonstrate it with log laws? How could you do a question like this on a no calculator test? Because you could. Even to change a base, you would need a calculator for this. Log of 10 divided by log of 5, that's not going to work. Does anybody know what to do here? Sure?
Isn't that just log base 5 to the times 10 times 12.5?
Okay, so log base 5 of 10 times 12.5. And it turns out that that works. Like it's obviously set up to work that way because that's 3. 5 cubed is 125. Okay, next one. Try this one on your own. Here's another neat way you can evaluate logs, think about logs using what we learned today. This is equal to log base 3 of 3 cubed. That's a bit confusing just written because there's a lot of 3's and we don't really know which 3 is which 3. But you could always take the thing you're taking the log of and rewrite it with the same base as the log. Like if you can do that, then it's just equal to the exponent. It's the same idea, But for some people, that might be a little bit more, I don't know, just the way that it clicks a little bit better for them. Let's try another one. Any questions about that one? That one okay? Everybody got that? Didn't go too fast. So I can think of several different ways of doing this one. See if you can think of a way to do it. And then we're going to do it several ways to just see how all of these things take us to the same place. And to me, it's not about doing it the quickest way. It's about all the different ways and using all the properties so we get to know all of them. See if you can find one way of doing it. People are thinking of all kinds of different things. It's great. Oh, I wish we could all walk around and see what people are writing. Okay, so here's one way. A few people came up with this. Log base 2 rewrote 8 to the 1/3. And that makes this 1/3 times log base 2 of 8. Now log base 2 of 8 is 3. So you could evaluate that to 3 there. That would be fine. But you could also use one more log law to go log base 2 of 2 to the 3, because 2 to the 3 is 8. And that used one extra. Could be like a challenge. How many log laws can you use to solve one question? Right? Some people might have done it the sort of way with fewer steps. If you know that the cube root of 8 is 2, I mean, you could just evaluate that. There's no rule that you're not allowed to do that. And that's just equal to 1. Right? Using one of the other log laws. Anyway, any questions about that? Yeah. Okay, one more. So again, I could evaluate 2 times 4 cubed. It's going to be fairly big, but not crazy big. But without, let's see if we can solve it without doing that. What would be our first step? Anybody have an idea? Very good. Log base 2 of 2 plus log base 2 of 4 cubed. Which equals log, I'm just going to leave that as log base 2 of 2 for now, plus 3 times the log base 2 of 4. So that's, hopefully the rest of this is fairly simple. Whoops, no, I meant to evaluate that, sorry. So log base 2 of 2 is 1 plus 3 times 2. Log base 2 of 4 is 2. 1 plus 6 is 7. All kinds of other roads you could have taken. So for example, right here, I could have changed this to log base 2 of 2 squared all cubed, which is log base 2 of 2 to the 6, which is 6, and then still 6 plus 1 would give you 7. Like, yeah, there's different ways of doing it. But the reason why I wanted to show this example is, and I know that this comes up in calculus, by the way, is when people start with this, okay, they take that 3 and they move it out in front of the whole thing. But the 3 is an exponent just on the 4, so it's multiplied just by the 4 part. Does that make sense? So just be careful of that if it comes up. It comes up a little bit in this class, but it also comes up in calculus. Any questions? I think we got 1 or 2 more examples. What's next? Am I missing anything? Yeah. Compare the following functions. This is really interesting. This is a functions class after all. And all the algebra we do is supposed to be supporting our understanding of functions. And what's one of the big things we talk about with functions? Transformations. So shifts and stretches, reflections, all that stuff. So, what can we do with these? Well, this one's like log of 100 plus log of x, right? So using the product law, what is log of 100? 2, because log base 10 of 100, 10 squared is 100. So this is like, if you want to add in an extra step here, log base 10 of 10 squared, which equals 2. Look, they're the same function. This comes up a lot. We don't always talk about it. So this is this is a vertical shift of 2, and this is a horizontal compression by a large factor, but they have the same impact, same graph. Where do we see this other places? Y equals 2x all squared. So horizontal compression by a factor of 2 is the same as a vertical stretch by a factor of 4. Or y equals 2 times, this is one that I like, 2 to the n. Same base, you add the exponents. So that's like, or 2 to the x, I should say. I don't know why I used n. 2 to the x. So that's an exponential function with a vertical stretch by a factor of 2. But if I add the exponents, it's 2 to the x plus 1. It's a horizontal shift to the left 1. Is the same as a vertical stretch by a factor of 2. Like things you might not guess, but turns out this stuff happens all over the place. Okay. This one's a good question just to, I think there's a few like this in the textbook. Could be one like this on the test. I think there's one on the learning goal tomorrow. Good one to practice to get all of our log laws done properly. Okay, so the first thing I'm going to do is I'm going to manage the 5. So this works out to log base A of x cubed y over z squared to the 1/5. And that 5th root was on everything, so it's still on everything. So I do take that one all the way out to the front of the whole thing. And you could probably do this in one step, but we're going to do it in 2 steps. So this is like x cubed y, whoops, missing a bracket, minus log base a of z squared. And then I can split it up even a little bit further. Log base a of x cubed plus log base a of y minus log base a of z squared. Just watch for a second. You'll have a chance to write this down, but just watch. It says in terms of log base a of x, of y, and of z. So what that means is like no exponents. So we have to take this one step further where we get the exponent out. Now it's 3. See, because now I have log base a of x on its own. That's what the question is trying to ask you to do. Get it all the way down so you just have that part. Plus log base a of y minus 2 log base a of z. So that would be done all the way. I've got log base a of z separated, log base a of y separated, log base a of x separated, no other junk in there. I do have other coefficients and multipliers, but you don't have to multiply the 1/5 back through or anything like that. Nothing like that. Any questions?